Okay, welcome everyone. And you might hear a few pings as I'm getting people coming into the lobby. Thank you everyone for joining us today. I'm really excited to have everyone online today. Um, this is as I mentioned, let me go full screen on this so people can see. This is the inaugural seminar in our new seminar series. Just getting this squared away. One moment. Yeah. On complex risk science. I'm really delighted to have everyone here, and I think that each of you represents a community unlikely to be brought together elsewhere. And that's really the purpose of these events, is to bring together people that span the space of knowledge and capacity that are going to be needed to consider complex risk science and kind of create what I'm thinking of as a collective that is as plural as it is rare for this. So my name is Ryan McGranigan. I know many of you, maybe not all of you, and I'm excited about that as well. I'm a researcher here at the NASA Jet Propulsion Laboratory, where we're hosting these seminars, these virtual seminar series, and I'll be kind of curating these events alongside a few other people as well. So today I'm going to provide a little bit of framing. I'm going to be a bit longer in that framing than usual, just to kind of set the stage for everyone, as this is our inaugural event. But we're thinking of this as exploring new frontiers in risk science and a new community for understanding risk. So I'm very happy to have everyone here, and thanks so much. Please feel free to use the chat. I've posted a couple of links there for our website and in a Slack space where we can interact between these events, and really happy to have people interacting there as well. So real quickly, kind of a background on risk science. Many of you are I'm sure, familiar with this, but just kind of as a primer. Risk has this kind of seemingly simple equation of likelihood of some natural phenomenon or hazard times the exposure, the things that are standing in the way of that, the propagation of that hazard or phenomena, and then this term vulnerability. What is the susceptibility of that piece of equipment or that population or some part of that system to failure or disruption as a result of that. Adam Sobel is a colleague of ours from Columbia, and he's someone who I've learned a great deal from about risk science. And he has this kind of definition of what risk science is: it's the set of approaches and research areas that bridge from the fundamental understanding to concrete and quantitative impacts that inform decision making. So if you think about it from that perspective, risk science is kind of this requisite literacy for what we're trying to do within science now, which is kind of move our knowledge towards how we can impact society in a positive way and improve resilience and well-being for society. We have a lot of background and framework and foundation for risk science. It is risk studies is a whole field in and of itself, and disaster risk reduction is a really well-developed field as well. And a colleague of ours, Jane Baldwin, in cooperation with Adam as well, has kind of a great example of a kind of an end-to-end risk science analysis that I just wanted to highlight. It's from a paper in 2023 where they looked at the hazard. They're looking here at tropical cyclones, and they simulate under changing climate scenarios the intensities of those hazards and the tracks of those winds for different tropical cyclones as they impact. In this case, they were studying the Philippines. And so you can see how they're kind of aggregating that information. And then they have a map of the exposure. These are households in this study that are in the way of these tropical cyclones and the winds that they experience, the intensity of those winds that they experience. And so you can see how those maps lay out spatially. And then this kind of seemingly simple but very actually complex parameter called vulnerability. This is kind of mapping those hazard intensities, how much, for instance, in this case, wind speed maps onto the fractional damage or loss or failure of the pieces of equipment that you're looking at. That's a very difficult relationship to develop. But these vulnerability curves are very important. Once you're able to put all these things together, then you can actually start to study the relationship of how intense the event you're experiencing is to the asset losses or the failures that you might experience. And then you can also study how those failures then lead to other failures and things of that nature. And this is a fantastic study. And to be very clear, our risk science is well developed and there's an excellent foundation on which to build. But for the sake of this seminar series, I think that we're doing risk science wrong. I think in many ways what we default to, and this is not obviously generally the case, but what we're defaulting to is studying hazards as independent hazards. We're studying them separate from one another. For instance, how do wildfires and winds operate differently? But if you look at places, anywhere you look really. But if you look at the World Economic Forum, they publish this global risks landscape map that shows how all of these things are interconnected. All these systems are actually interconnected. The strength of their interconnection. How well do we know how much they influence one another? And you can see that our economic systems, our societal systems, our environmental systems, they're all intricately interconnected and complexly interconnected, that we need to really start to consider in what ways they influence one another, and kind of the temporal cascading and the spatial intersection of those. What we understand now is as a result of many studies that have been done lately, we understand these interconnections alter the risk landscape in non-intuitive and many times non-linear ways. So there's a great study in 2010, it's kind of a landmark study, where they looked at the power grid system and the internet connectivity systems as separate, independent systems. And so if you look at the independent network, this is kind of this blue line here, you have this kind of general fall off of the behavior of the capability of the system. And I don't want to describe this study in full, but you have this kind of gentle fall off. If you then layer those on together and understand their interdependencies, you have a first order phase transition that happens that's not predicted by the independent network. And so there's this very critical understanding of that's only possible by understanding by studying the interdependent network. Much more recently, in our backyard here at the Jet Propulsion Laboratory, there are now, by many measures, the most devastating wildfires the U.S. has seen. The Palisades and the Eaton fires back in January, and one thing that happened as a result of those is we kind of looked at the risk maps that were drawn for those. If you look at the one that was used for our preparedness measures, that's kind of in the shaded red here. That's the Cal Fire risk map that took into account the wildfire conditions only, and you can see that the highest severity zone stops at the edge of Altadena. Now, if you look at more complex models, which were available, but maybe not trusted because of the complexity that they include, they identify, and that's kind of in the red lines here, they identify Altadena as in the highest risk category. That has a number of very important effects when you identify an area as a higher risk to these hazards in terms of preparedness and how we understand the response to them. So these are very real, tangible things that are happening, these interconnections. They're altering risk in ways that we need to understand. That's kind of the central question of these seminars, is what do the interactions do to our understanding of risk? So a field that has been studying this for a while, these are socio-ecological technological systems, sets, and it's a rich domain of science. And I think that they identify some of the key interconnections that we're trying to understand here. So when I say that we're doing risk wrong, it's just a matter of trying to understand how do we maybe evolve this towards a complex risk science, an approach that is driven by some of the ways that we think about complexity science, which is really the study of a system of interacting elements and what emerges from those interactions that may not be a part of just a simple sum of the individual elements. This is what allows us to study critical transitions and really get to a resilience mindset and understand how systems are or are not resilient. So it's a matter of understanding the interconnections between hazards and infrastructures and the way that those alter risk. That's kind of the central question for what we're talking about here. So I'm not going to belabor this. You can look at the website and see things, but I did want to talk about, I have given a little bit of description of why we're doing this, but the kind of making it very explicit. This requires a very plural perspective, a lot of capacities, a lot of knowledges, a lot of capabilities to study this and to actually bring these things together. And these are, as to the plurality, that's not going to happen naturally. And so this is a deliberate attempt to kind of bring those communities together. This is a sub-seminar series that's kind of emerged from something called the Science Understanding from Data Science, or SUDS initiative. It's something we led for 3 years at JPL. I'll say more about it in just a moment. But it's now emerged into kind of a multi-institutional movement, and this is one of the Horizons initiatives that's been identified within that. A couple of ways to connect with this. You can contact me if you just want to talk about it. We have an open SUDS network Slack channel for announcements and interactions. Feel free to join there. And then the QR code here is to the website for the seminar series. These are going to be bi-weekly. They're all going to be virtual for now. We're going to experiment with this from September to December of this year. To convene this community, and then we'll reassess and figure out what is useful, what's not, how do we shift and pivot this, and what would be useful to everyone here. You can see a few of the speakers that are lined up to join us. Really an exceptional group that's been giving thought to these things, and I'm very excited about that. And there'll be more to be announced. So if you have ideas or if you'd like to be a speaker, please let me know. You can reach out. So a very brief background on the Science Understanding from Data Science. This was an initiative within JPL to increase the speed, depth, and rigor of scientific return by revealing new connections through data science. It was trying to unite 6 distinct communities, which were physical sciences of Earth, space, and planetary science, and then 3 distinct data science communities, so model-based inference, machine learning, and uncertainty quantification, and try to bring all those together to how we improve our knowledge of the physical science systems. We held an inaugural workshop with institutional leaders back in August of last year. And what we did identify and understand was that there was broader ambition in the work that we were doing was needed to kind of really spark SUD's work to get this to be considered and brought into to the mainstream. We established risk science through that as a horizon of this, a horizon initiative. So this required multi-institution, multi-sponsor, and had to be grand enough to inspire the community to really organize behind it. That's one of the motivations for this. So this is a bit of a timeline of what this seminar series is building on and what it's building towards. So it builds on the SUDS initiative and the workshop and conference. It builds on a fantastic JPL Climate Risk Science Workshop that was held in October of last year, and I can provide a link to that. But I mentioned Adam Sobel. He was integrally involved in planning and convening that. So it does very much build on that work as well. There was a workshop held earlier this year at Princeton called the Critical Transitions in Socio-Ecological Systems, where the community is still organizing and interacting around that. We held a Boston Area Complex Risk Science Summit, the first of its kind, in June of this year, which was exciting and generative as well. What is building towards? It's building towards, concurrent with these seminars will be a series of analysis working groups that were identified by that Risk Science Summit that are going to be organizing around specific curated data sets to make progress towards these things, understanding how do we do complex risk science, how do we actually organize and connect across institutions via these objects that are the data sets that are kind of uncommon for that. We're working towards a workshop that's going to be held at IASA in October, which is really exploring this idea of epistemology of risk and resilient science, which is very exciting. And I don't think there's been an event quite like it before. So props to many who have been involved in planning that are online here. We have an AGU session this year called Navigating Risk in the 21st Century, trying to articulate these things and bring together the frontier research on this. And then hopefully in June of next year, we'll have some sort of JPL Complex Risk Science Summits. So we're building towards that as well. So a key to this is cultivating forums for us to continue to interact. I mentioned the Slack channel. Please continue to join these complex risk science seminars. These are open broadly, so please do invite your colleagues and people you think would be exceptional to these. It's all building towards this idea of what I've been calling fractal gathering. In an age where it's maybe increasingly difficult to gather, at least here in the US, we need a way of kind of cohering this community serendipitously across media, across institutions, across scales, and allowing those interactions to build to something more than the sum of their parts, which is kind of the general idea for fractal gathering. But we'll be doing that in a number of ways. I like this quote from John Dewey, just in kind of bringing this to a close and handing it off to our seminar speaker today. We lie, as Emerson said, in the lap of immense intelligence, but that intelligence is dormant and its communications are broken, inarticulate, and faint until it possesses the local community as its medium. So hopefully this can be that for a local community. What these are going to be community and capacity building. They're open and collective and generally an ethos of inquiry and open questions with one another. They're plural, pragmatic, and generative. What these are not are going to be performative or kind of marketing, just kind of circulating the latest things that we're doing, but it's really more discussion oriented. They won't be exhaustive, but they'll hopefully be provocative, and they won't be final or settled as well. So just setting little expectations for these. So I can think of no one with these thoughts in mind, no one better suited to kick off these seminars than Dr. Arup Ganguly. Our speaker today is Dr. Arup Ganguly from Northeastern University. Dr. Ganguly is a College of Engineering Distinguished Professor at Northeastern University in Boston, where he has been on the faculty since 2011. He has founded, leads, or co-leads a number of initiatives at Northeastern, including Director of the Sustainability and Data Sciences Laboratory, Co-Director of the Global Resilience Institute, and a member of one of the core leadership team for the Institute of Experiential AI at Northeastern. In the ethos of being interstitial, Arup works at the nexus of climate extremes and water sustainability, infrastructure resilience and homeland security, and artificial intelligence and nonlinear dynamics. He develops fundamental insights about weather extremes and sustainability, innovative ways to reduce fragility of infrastructures, and new adaptations for data science for the challenges of our changing world. He's the author or co-author of hundreds of publications and is the co-author of the book Critical Infrastructures Resilience, Policy and Engineering Principles. And I've been attracted to Dr. Ganguly's scholarship for many years for some of the frontier work that he's been doing. But perhaps more than his research, I know Arup to be someone endlessly curious about the world and the people in it. Despite all that he's accomplished, he has a humility that is suited to the idea of risk science, and which makes him not only a researcher who creates breakthrough discoveries, but also a fantastic mentor and teacher. So without further ado, it's my great pleasure to invite Arup to share his work with us and to ignite this complex risk science seminar series. So Arup, over to you.
Well, thank you so much, Ryan. I'm not sure I'll be able to do justice to all that, but in the interest of just setting up some of the discussions, so let me first share the slides. Can you see the slide?
Yes, that looks great.
And can you see it in just one second, slideshow mode now?
Yeah, we're seeing the
All
full
right.
screen.
Okay. So thank you so much, Ryan, for setting that up. This is a wonderful opportunity. And in that spirit, what I'll have is more of a try to initiate some discussions. Given that this is a very interdisciplinary audience, I'll cover a few things, but I'll cover them quickly here rather than going through depth. Of course, I have the citations and such if you're interested. And I think Ryan made a very interesting point. Given the complexity of the world we are facing in, we have to be humble to what we can do. But that being said, collectively, I think we can do a lot more than any of us can do alone. So first of all, here are acknowledgements to all my funding agencies. And with that, let me start with a very quick math refresher, which I often do in some presentations like this, recognizing the very different backgrounds of the audience. So we are familiar with deterministic equations. So on the left, I have the constant velocity equation, dx dt equals v. Very simple equation, which says that I move with constant velocity, and here is what happens in terms of space and time. Now, if I transform that just a little bit, it's still a deterministic equation, still an ordinary differential equation, dx dt. I have two other variables, y and z, and I have these dx dt, dy dt, dz dt as functions of x, y, z. It's a simultaneous ordinary differential equation. It's an idealization of the weather system, but already we see complexity emerge. The person who found or rediscovered some of these things, I would say, and definitely discovered this in the context of weather and in modern times, had this quote: when a butterfly flutters its wings on one part of the world, it can eventually cause a hurricane in another. This is Ed Lorenz. That was to illustrate partly the fact that, okay, we have these things called strange attractors, which do resemble a butterfly's wings. These days, these kind, and they are extremely sensitive to initial conditions. We see living examples of that these days, often in for example, hurricane tracks, where you have these spaghetti plots, and they do impact in some ways climate as well, and we are learning more and more about that. So if that was deterministic, but an example of complexity in deterministic system, here is an example of complexity in random systems. On the left, I have possibly the simplest of random systems, just Gaussian white noise. So you sample from the Gaussian distribution and do not preserve any memory. And on the right, I have this almost the same system with just preserving the memory from the last time. So it should be the other way around. I'm sorry, xt plus 1 equals xt plus epsilon t, or xt equals xt minus 1 plus epsilon t. But anyway, these kind of systems can lead to this whole complexity of behavior, which you would think that just from this ordinary Gaussian would not be feasible, but here you go. And if you were to combine those two, if you were to say that, okay, I have this constant velocity term, for example, and add a little bit of jitter, stochastic jitter, and you could do that in the context of, for example, Lorentz systems, the one I was showing earlier, I mean, add different kinds of jitter in addition to Gaussian white noise, we would get very interesting results depending on the signal to noise ratio, if I can call it that roughly. We could get things that look very random or fairly deterministic and all kinds of combinations. The other kind of math that's important and interesting in the context of risk analysis is understanding rare events and extremes. So for example, we have extreme value theory where we try to infer about properties of things like 100-year levels, which are just 1 over 100, 1% probability, for example, of storms. And what we do is we look at the high values, but not so high that we don't have any data, but high enough so that we can approximate some, or we can infer about some properties of these extremes. And we use various approaches and various specialized distributions to do that. This has been a field that statisticians and hydrologists have been working on for a while to get return levels. This gives us things like likelihoods for certain events, which we can then infer from either from observations or from models or combinations thereof. The other thing is we are worried about extremes in this day and age that we live in. We seem to see one extreme after another every time. But we are more worried about extremes because we are so interconnected these days. Uh, whether it's natural systems like climate systems, which have always been interconnected, or human engineered systems, which are getting more interconnected, or even social systems. The thing is, though, these interconnections give us mutual strengths, but these interconnections also have fragility patterns that make all of us vulnerable to major and catastrophic failures. And one other tantalizing possibility, though, is just as we have these the possibility of catastrophic failures, we also have this possibility of simultaneous recovery when something happens, and they may not exactly follow the trajectory of each other. The other thing in terms of these interdependent space of risks, this is something we have been getting, and when I say we here, I mean collectively as a community, of course. We've been getting a bit better with trying to understand that. Here is one set of tools for exploring joint dependence. These are called copulas. And as you might see from some of the shapes, some of these copulas are geared towards understanding what are called tail dependence or dependence among extreme values, which might happen if there are a combination of extreme hazards, for example, or even combination of a threat with vulnerability, with exposure, I mean, dependence patterns among them. These are just one set of tools. There's an interesting digression that some people blame the 2007 and 2008 financial crisis on the Gaussian Copula model. Of course, it's an over attribution, I think, but it did the problems with using that. There is nothing inherently wrong or right about just a Copula model, but the problems with using that in the financial world caused a lot of hiccups. So interesting tools, but to be used with care. Okay, with that quick mathematical refresher, now let me come to some examples of what I mean by complex interconnected systems. Within one city, when we think of an urban of our urban infrastructure, we have a network of networks. Some would call that multiplex networks. So we have transportation, power grid, financial sector, communications, water distribution systems, etc., and all interconnected in the sense that failure in one would impact the other. So if power grid fails, for example, signals and systems fail, and then in urban water, the pumps might fail. So there is this cascading impact. And the issue is, could we still design systems so that they are resilient? And if they do fail, when they do fail, could we recover them in the best possible way? One other example of such networks comes from ecology. This is plant pollinator networks, for example. And we have many examples of those, and they are incredibly important, whether it's for food security, whether it's for horticulture, agriculture in general, etc. And of course, biodiversity. Here is one other example. This is from 2012 in India, where we'll see a lot of cascading effects that happened. And in 2012, there was delayed monsoon and significant heat waves just before the monsoon. What that meant was less water uh, during this initial period. India has had this history of green revolution where farmers have been incentivized, and continue to be incentivized to extract groundwater for agricultural usage if needed. And this has helped a lot. This is a well-meaning policy to help in food security, and it has helped there. But the unintended impacts of those policies are that farmers don't want to take any risk. So even if later the monsoons eventually catch up, the farmers want to extract groundwater. What that implies, of course, is that it's a huge stress on groundwater resource. And then all of this electricity that is used across the rural regions of India, together with electricity usage in urban areas, cause increased stresses on power grid at various places. When that happens, one or the other place might break. And in 2012, this led to the North India blackout, which probably still remains the largest in terms of population impacted. And when that happens, of course, because of the interdependencies, the power grid failure then impacted Indian railway network, which is one of the major lifelines in that country. So from natural system, monsoon and heat waves to um, human policy decision-making systems in terms of policy incentives, groundwater extraction, to human engineered systems. So you see all of these, how they are interconnected and how this becomes incredibly hard. We have, we are all familiar with what happened with New York City and Hurricane Sandy. And right after that, New York Times came up with an interesting article on how to build interconnected nature-inspired solutions to prepare before the next storm. And the level of interconnectedness in the context of Sandy is shown here. This building that's lighted up is the Goldman Sachs building. And Goldman Sachs were a little bit more prepared to the floods and storms that may happen after Hurricane Sandy. So no wonder they were lighted up. In fact, relatively speaking, they were so well prepared that they were the one lighted spot in a dark city. However, because, as they say, that you cannot build an island of resilience in an ocean of fragility, that's just a saying. What happens here, what happened here is that Goldman Sachs building was up, but Goldman Sachs business depends on people going there. And because everything else was dark and flooded, people could not get to the Goldman Sachs building. So this shows the interconnected nature. Even broadly speaking, we have in these kind of systems what some of us have been calling a convergence of complexity. So we have chaos and natural variability out of which all these extremes and other things emerge. So in the natural climate system, we have the potential of cascading failures. Things are interconnected, cascading failures, but potentially also simultaneous recovery in lifeline infrastructure system and ecological networks. And here is an example of from Italy. And then here is the US national airspace system. And then in complex social systems, we have this issue of tragedy of the commons. And, professors such as Elinor Ostrom, they have studied how these systems behave, talked about the need for polycentric management. And we have also looked at how policy myopia and financial disincentives can lead to engineering stagnation, outdated best practices. But the good news is, or at least our thesis is, that even minor efforts in financial incentives and transformative science can lead to this vicious cycle being sort of changed to a virtuous cycle. So it's complexity in natural systems, human engineered systems, social systems, and then it's the interconnection of this complexity. Very hard problem to address. Let me come to one of those. So in the context of climate, for example, there are two sides to this. I mean, these days we hear about AI a lot, and AI is indeed a very important and emerging tool. But you also have to realize that in climate, just as we have this big data challenge, I mean, when we think of model archived model simulations. This is the orange band, and then remote remote sensors such as satellites and radar, that is the blue band, and then these in situ sensors. That information is also increasing, but not much compared to this. There is some debate these days on the exact amount of these data, but the point is that this data has been increasing and continues to increase. But in climate, we also have these little data challenges. And part of these come from the fact that when we go back into the past, and often we need to, there is not enough data. And when we are looking at rare events and extremes and stresses, almost by definition, we are dealing with rare data. I gave this example with climate and water, but just to emphasize, there are similar kinds of things about both big data and large data that happens in certain kinds of social systems, certain kinds of human engineered systems. And in human engineered systems, there's also this additional issue about security. So with that quick framing, let me give you a little bit of some action stories with risk and resilience. So very broadly speaking, here is what, here is how we think about risk, and Ryan has already done that framing. We talk about probability of hazards or threats. We talk about vulnerability, which is probability of damage given a hazard or a threat, and exposure or asset, which could be quantified as in terms of dollars or human lives. And risk then becomes some combination of these. Some people denote that as a multiplication just for convenience, but the units remain the units of exposure, and this can be called as expected loss. So if you're thinking about, let's say, building some infrastructures to enhance resilience in New York, whether this is nature-based system, whether this is hard infrastructure or a combination gray-green infrastructure, we are talking about balancing that investment with what it means for the benefit, not just in one given year, but year over year. So the one start for that is the kind of engineering economy analysis that we do. But the other thing to remember here, as Ryan was saying, that these threats are not necessarily independent. So if we have a hurricane, we might get into situations of riverine floods. We might also get into storm surge kind of flood. So and that's just one example. So storm surge or coastal floods, but there could be hot situations and dry situations. So all kind of compound extremes. And again, if you go back to that quick mathematical treatment of how we can deal with tail dependence, Copula is just one example. Those are the kind of things that come to mind. But it's not just within the compound threat themselves. It's also in the space of vulnerability and exposure. So let me give another example, and I know security is not maybe one of the main interests here, but just in terms of, just to give an example, if a place, if an airport or a seaport or a subway system is made less vulnerable through investments in security, what that also means it becomes less attractive for somebody wanting to create harm in that place, because there is more work that needs to be done, probability of damage is less. So vulnerability and threat are clearly, in that case, related to each other. The same example can be made in certain kinds of flood systems. For example, Mother Nature may not care about vulnerability, but the kinds of things we do might impact that we do, for example, in terms of land use, agriculture, urbanization might impact the probability of floods, etc. And same with exposure and things like urban forms. So these are sometimes thought to be independent, at least for our conceptual understanding. But it's not just compound threads that are interrelated with each other, but all of these things could be interrelated, and that makes the problem a bit complex. So here is the IPCC, the Intergovernmental Panel on Climate Change, who took that broad risk framing and put that in the context of climate. So the example that's probably maybe easier to understand is the example with hazard, let's say Hurricane Sandy, or before that, a Hurricane Katrina. So all of these hurricanes, and I'm just giving examples with hurricanes, the same could, similar kind of examples could be thought of for the floods in Texas or Tennessee, just as an example. So we have a combination of natural climate variability and human contribution to climate change, the combination of which in some form or the other leads to these weather hazards. So there is already human intervention or human contribution, of course, built in here. But even those hazards may not be enough by themselves to cause catastrophic disasters. They need to impact with vulnerability and exposure, such as how good are our protective infrastructures, whether these are dams, levees, whether these are nature-inspired systems, such as room for the river to breathe, and exposure in terms of are these hazards happening in places where we have a lot of human habitat, for example, or agricultural land, other kinds of assets, biodiversity, etc. So it's a combination of this that leads to risk and impacts. And one thing to do, of course, is when these impacts are happening is emergency preparedness. And when I say when they're happening is just before, during, and just after in terms of recovery. But longer term, we need to think about adaptation, which is how to deal with some of these events. Adaptation has been called managing the unavoidable. And then we also need to think about longer term mitigation in terms of emissions and land use change. This is mitigation has been called managing the avoiding the unmanageable. So in this context, I'll give a few examples now. So we deal with climate projections such as Earth system models. We need to understand the knowledge gaps that exist, the irreducible uncertainty that exists, and in certain cases where AI-based translations may be feasible. And these are just examples that I'll give. Not everything, again, is about AI or is about these things, but just to inform our discussions here. And in the space of climate projections, Earth system models, when we are trying to understand how climate contributes to these things, for example, to 100-year rainfall events, we are primarily talking about informing design and policy. And then when we come to the adaptation space, there's a whole lot of things that needs to be done, from engineering, governance, socioeconomic pathways. I'll just talk about one of them, which is weather prediction. So if we think that rainfall may intensify because rainfall extremes may intensify because of climate change or hurricanes, the more intense hurricanes may grow even more intense, etc., then we have to prepare for them. And one aspect of that preparation is to get some of our prediction right. So I'll talk about that a little bit with physics integrated AI, how we can work with stakeholders. And when we talk about these are primarily designed to inform operations and planning. And I'll give a couple of examples after this on translation to decisions. The example I just talked about here is in the context of natural disasters, but I'll also talk a bit about public health in urban areas and energy security in the context of water energy nexus. So this example talks about how do we look at the multiple Earth system models that we have these days. We have about half a century of those modeling groups, and each modeling group may produce one or more in a coordinated manner. So one way is to look at model skills, how these models do in the when compared to observations in the past or in current conditions. But that may not be enough because conditions may change in the future. So which model will work in the future is hard to predict. That's why, we don't have observations in the future at least, so that's why you at least have to look at how these models agree with each other, where they agree more, where they agree less. That's called consensus. So we have to somehow balance between skill and consensus. But one other thing is, in certain situations, we may have information, we may have certain kinds of physics, we may have information available which are either not so well included in the current generation of models or maybe hard to include. And those kind of physics and even some correlation studies could then help in certain specific cases, such as if we understand a little bit about the physics of precipitation, then the combination of skill, consensus, and physics-based insights may help us in probabilistic modeling, such as in the context of river basins. We can also look at all of these models in more detail and try to see how these models perform across the world. and see, this was a recent work which looked at all of these models in terms of their parameterization schemes, comprehensiveness of physics and resolutions, and try to see what this means in terms of changes in runoff, and just compare them with population, human development, and GDP. And one thing that was found is that some of the quote unquote best models seem to give the worst case projections. And there is also a lot of complexity here. So the 6 that are unshaded here are 3 US-based models and 2 initial condition runs. These are very small changes in initial conditions, such as 10 to the power minus 14 in 1870. You would think these models would give somewhat similar results for water resources. This is P minus E, decadal average of P minus E subtracted over 30 years. So this is sort of the state of changed water resources. Not only do these models give different results, but also these initial conditions give different results. The shaded portions are the averages. So one on the bottom right is the average of the average. And what it shows is that the average of the average seems to suggest that not much change is happening. But of course, we cannot design based on that. We have to design for at least some of the worst case floods and droughts that may happen over time, rather than just averaging them out. So again, complex systems where managing this becomes an issue. But it's precisely these attributes of these complex systems that can sometimes help us get to some interesting insights, such as despite all these complexity in these initial condition runs, we can start to understand how they behave in terms of their dynamics and how they may be similar or different. And that kind of thing may lead us to certain calculations of extremes. So extreme value theory relies, or the kind of extreme value theory we often use, relies on this assumption that the high values, not the entire time series or space-time series, but the high values, they are IID, independent and identically distributed. And if that is the case, then the initial condition runs, which are from the same model and same forcing, so the inherent dynamics or physics is the same, could we combine all of that in our estimate of extreme value? And what we found is that indeed we can. And when we do that, instead of, let's say, 100-year levels and 30-year levels getting sort of difficult to distinguish in terms of confidence bounds, we can start to distinguish them. So while these initial condition runs were designed to understand what has been called natural variability by some, irreducible uncertainty by others, we can use those same initial condition runs to get better at certain things that we care about, such as extremes. One other thing that's also incredibly important in the climate context, and Science Magazine ran a news article about this, about, they called it hazy predictions, how cities need answer fast, but it's very hard to get to those with current generation of models. So we need downscaling. There are various ways of bringing these low resolution climate model simulations to the kind of resolutions that stakeholders care about. This is where artificial intelligence, such as computer vision, has been able to make certain breakthroughs. And not just that, explainable AI. So one part is downscaling in that given region. The other part is that there are these data sets, across the world's oceans and land, some of which impact things that happen. So, for example, regional hydrology at one place. So trying to come up with explainable deep learning to get these insights and overall improve, whether it's hydrology or whether it's statistics of weather at scales that stakeholders care about. These are, again, just some of our work, but there is a whole community trying to do some of these lines of work. But these showcase some of the things we have done in AI in terms of discovering some of these insights and trying to translate them to things that matter. But I'd also like to, again, go back to that big data, little data challenge that we have in climate. So not everything can be AI, and some of these things that I showed with extreme value theory, they at least start by recognizing the fact that that those are problems for which we'll never get into these big data kind of situations. Coming to the weather prediction problem, like I was saying, if we think that rainfall extremes might intensify under climate change, well, in that case, we need to adapt to these rainfall extremes. And one significant part of the adaptation, which we have learned from our stakeholders, such as the Tennessee Valley Authority, is just getting the short-term precipitation nowcasting right. So what we look there is when we used hybrid physics AI systems, this is AI systems but informed by physics, we found that these systems, at least in the short term nowcasting frame, can work significantly better than some other baseline approaches or even numerical weather prediction models, which the Tennessee Valley Authority, for example, now is testing on their operational system. But it's also important to realize that these things must be made trustworthy through the kind of metrics that stakeholders would like to see. So just going a little bit to a couple of other areas to demonstrate the usefulness of these risk framing. The town of Brookline, Massachusetts. So we did some work with Climate Ready Boston in terms of temperature extremes. Based on that, AGU, American Geophysical Union, and town of Brookline, they wanted us to do some initial work on risk framing of in the context of public health with respect to urban heat waves. So that framing is interesting. We still have global warming with natural variability and anthropogenic change, but we also have the urban heat islands, some of which are in the control of the urban planners. So when we think about global warming, that may not be in the control of each individual urban planner. I mean, they may be able to contribute if they are a large city. Certainly, collectively, they contribute. But within the context of one city, there are things like vegetated open spaces, green roofs, water bodies, etc., which they can do. So it's the combination that leads to the urban heat waves. There are various aspects of which kind of people are potentially most impacted by these heat waves, what kind of infrastructures are needed to ensure accessibility, for example, to medical facilities, cooling centers, and then the exposure in terms of people and infrastructure, and how that leads to emergency and medical services and adaptation. And in terms of the mitigation, it's almost two kinds of things that happen here. One is the tax that each city needs to pay. I mean, that's an analogy in the sense of overall greenhouse gas reduction. The other is the mitigation in the urban context, which is city planning, vegetated open spaces, etc. So a very interesting, a lot of interesting and important work needs to be done in these areas. The other work that we did for the US Department of Energy, and this again is just one example, is how to look at water stress in the context of power production at risk. And here the need is to understand both rising stream temperatures and changes in net water availability in the context of power plants. But with all of these different kinds of complexity, all of these scenario-based climate runs, the multiple climate models, and the initial condition runs, all of these, how they relate to the potential for each region or some regions with installed power plants getting to these scarcer water and warmer water kind of scenarios. Just wanted to quickly talk a little bit about beyond risk. Some people have been starting to talk about resilience. I mean, I don't think it's that different, but it takes this risk paradigm, threat, vulnerability, exposure, and says that, okay, we need to think of a system in terms of the function it provides. So for example, transportation provides accessibility. And while certain kinds of, let's call them white swan events, certain disruptions are normal, but we can work around them. But we care about these large disruptions, and we have to think about the response or the fragility of this system to that, and think about graceful degradation of those functions so that we don't lose the critical functions, and then how we can recover these systems, and whether we can get to a stage where we learn from these from each of these disasters and get to a better state than where we started from. We have looked at some of these, for example, in the context of urban metro rail systems across the world. So Washington, Boston, Chicago, Paris, London, Shanghai, Delhi, Tokyo, New York, etc. I'm just emphasizing, I'm just showing our work here because that's the one that I know better, but there is a lot of work that has gone into this space. This is an interesting work, again, with New York City post-Hurricane Sandy. This is New York City MTA, the mass transit system. And what we found there is that the total loss in recovery or total loss in revenue during the recovery period was about $124 million. And the process was very ad hoc and disorganized. But what we saw is that even to a first order, if we could have an organizing principle, such as with network science, we could have reduced half that amount in terms of revenue loss. So half the amount from $124. And this is, one of our other studies with London Metro emphasized that even further. I know the emphasis here is primarily on weather, physical space weather, Earth weather. But here the example was with flooding and security kind of thing. So just to give an example of, the kind of, one set of complex or compound threats. So in the London Metro, we have seen both, flash floods, and we have seen man-made attacks. And we tried to explore these hypotheses that to try to overbuild for resilience, sometimes we do not think so much about, to overbuild for efficiency, which has always been the case. Sometimes we don't think about resilience as much, such as some of the major railway stations in this urban metro may be near the rivers simply because that enable movement of cargo, but that may not be best in the context of resilience. The other thing we're trying to explore is the combination of these compound attacks. Do they in some way create more failures, so where the whole, in a sense, is greater than the sum of the parts? So those were our hypotheses, but we looked at the London Metro in terms of both the flood maps and how these are situated. Here is the whole London Metro. It is a multiplex network of networks. We looked at both floods, the failure because of flood, and the combination of floods with targeted attacks, and how these profiles change to Ryan's point, and then overall how these, after one of these failures or these multiple failures, what are the best pathways to organized recovery. That was the kind of thing I was illustrating with that demo in the context of New York City MTA after Hurricane Sandy. So I'd like to end with a big thanks to all my students, postdocs over the years and now, and some of the big support we have received from the various governments, including Boston, Massachusetts, and of course, various world bodies. With that, thank you so much. I know I was rushing a bit, but hopefully this will spawn some discussions.
This is fantastic. I'll collect slides from you if you're comfortable with that, and be sure to post those. We do have a number of things in the chat, so maybe we'll start just from the top and we'll get to what we can. If not, we'll move things over to the Slack channel and we can continue interactions there. So Kevin, I know that you had a comment that I thought was fantastic. So do you want to open your mic and ask that, or I'm happy to read it if you prefer?
Sure, I can describe it. Yeah, great discussion. The thing that the one question I want to have is really about the observability of a system if you're concerned about risk-informed assessment in the way, or fragility. So an example I'm thinking about is if I have more detailed understanding of, say, the resilience of a forest under drought conditions, I should be able to predict better whether or not that's going to be flammable and then how much if it does flame. If I have a certain saturation of soil, I might be able to better predict whether or not I have the probability of that flood occurring. So I was just wondering whether or not in your framework you described like the probability of damage given hazard. Now sort of expanding that to the probability of damage of hazard and then conditioned additionally on observations, such that could we ask the question, if I change the network by which I'm making observations of that system, would I be able to better change the probability distributions because I have a better, less uncertainty into that calculation?
This is a very good question, and there are communities looking into this, including us, but also a big community, both in the context of natural assets, such as, like you said, forests, etc., but also in the context of human-engineered systems. So one thing is, of course, we need to, a lot of thought has gone into there are certain kinds of hazards which cause some damage to functionality, but we can live around that. This road is flooded, we take another road, and we basically still achieve the accessibility function, for example. And like you said, some systems can absorb those. There is some work going on in the community as to how to explicitly build for those kind of resilience, so that what we currently call or currently may fall in the category of gray swans in the context of their impacts, could we transform them into white swans because okay, we can live with them. And this is especially crucial when we think about what has been called graceful degradation. So for example, okay, we might lose power, and we'll try not to lose power, but sometimes we may still, despite our best efforts, but could we at least ensure that in the ICUs we don't lose power so that people don't have to die? So work like that across natural human engineered systems is happening, including exactly what you said, explicitly building for some additional resilience, both in terms of being able to absorb the shock and become more fragile, but also being able to recover. That opens up a very big discussion point, but just as of now, yes, absolutely. This is very important. People are looking into some of these aspects. I would say not all of these aspects. So there's a lot of things that needs to be done.
Great, thank you.
Thanks, Kevin. Arup, we'll do one more, and then we'll probably be at time here. So the question is from Dion. Dion, do you want to ask your question, or do you want me to read it?
You can read that. I'm okay with that.
Okay. So she's wondering how a delayed monsoon onset, perhaps in India, influences the cascading interactions among climate variables, and kind of how does it amplify risks of various types?
Yeah, so it's both climate in the sense that the monsoon is a very complex problem, of course, as we know. But there is the onset of the monsoon, which some people have empirically related to the overall monsoon rainfall that India may get, etc. But also there is the part of the monsoon that happens towards the end of that season. It's a 4-month season, which is more driven by, at least a quarter of that is driven by precipitation recycling. So the rainfall that has already fallen on the land and the vegetation that is recycled. So in that sense, yes, all of these things, how they form, how these monsoon rains happen, how much happens when, has implications on climate, has implications on the land atmosphere interaction. But also what I was trying to show is because of the various policy constraints or incentives that have been put in place, usually they are all well-intentioned, but because of the way they have put in place, there are unintended consequences, such as farmers drawing more water, leading to more electricity, but also leading to groundwater abstraction, when maybe if we waited for a little bit longer, maybe it was not necessary. But because of all these things, they're happening. So there is an impact. And then I talked about impact on human engineered systems. So yes, there is impact on the climate system, especially on regional climate. But also there is this impact on human engineered and social systems. A lot to discuss there.
Fantastic. There's a couple of the comments that I think are going to actually be meaningful to sustain discussion over in Slack. So I'll make sure I copy those over from Justin and Newton. Really poignant questions. So thank you for those. Join me in thanking Dr. Ganguly once more. Thank you all for making time for this first inaugural Complex Risk Science seminar series. Our next one is actually going to be 1 week from today, not 2 weeks. And Newton, I'll make sure you get the link to that Slack. And thank you all. Thanks again, Arup. We'll talk to you next week.
Thank you so much. Thanks for having me.
Thank you.